Hi, everyone. This is our first lesson in learning pre-calculus. We're going to cover functions and function notation during this section. A lot of vocabulary, and we have 5 objectives. So, we'll be able to determine whether a relation represents a function. We will be able to find the value of functions. Plugging in your input value and spitting out either a numerical output value or an expression as an output. Um, our third objective is determining whether a function is one-to-one, which is a special type of function. Uh, Remember how we can test functions by using our vertical line test, which we'll formalize during this lesson. Well, one-to-one functions are tested using our horizontal line test. And then finally, our fifth objective, we'll be able to really hone in on our toolkit functions, aka our parent graphs or our famous graphs like x squared, x cubed, the square root of x, the cube root of x, 1 over x, just x, or 1 over x squared, and what those look like from a visual standpoint. So let's jump into it. And I'm actually going to make this a little larger so you guys could see everything a bit better. Okay. So this first slide is really going into some definitions. We have our formal definition of a relation, where a relation is a set of ordered pairs, and the set of the first components of each ordered pair is called the domain, whereas the set of the second components of each ordered pair is called our range. We will be learning a lot about domain and range all throughout the pre-calc curriculum. They'll pop up pretty frequently. Just in short, domain is essentially all the possible inputs that the function can take in, aka all of your possible x values, whereas your range are all of your possible outputs, all of your possible y values that your function will spit out. And then we also have our formal definition of a function, where a function is a relation in which each possible input leads to exactly one output. And we say the output is a function of the input. All of our input values make up our domain, while all of our output values make up our range. And so down below, visually, we have a few visual representations of relations that are functions. And you can clearly see that the ones that are functions have unique x values, meaning the x values are not repeated, whereas a relation that's not a function, notice how an x value is repeated. Q is repeated twice. Your input Q will spit out either Y or Z. I'll give you 2 different values. Okay. So, how do we determine whether a relation is a function? Well, we want to be able to identify the input and the output values. And then if each input value leads to only one output value, meaning each input value is unique, there are no repeated input values, then we can classify the relationship as a function. meaning it passes our vertical line test. If there are repeated x values, then boom, our vertical line test fails. But if each input leads to exactly one output value, aka no repeated inputs, then boom, vertical line passes and we have a function. Let's jump into our first example where we want to determine if menu price lists are functions. And so we're given a menu here with plain jelly and chocolate donuts priced at $1.49 and $1.99 respectively. And we're asked, is the price a function of the item? Is the output a function of our input? Yes, it is. Right? Whatever we plug into our input, our output will spit out, aka when you're looking at our input values, our most common variable is x. These make up your domain in this case, right? And represents your independent variable. So they don't rely on anything, whereas the price does. The, the price depends on the independent. It's our dependent variable. It's our output, our y variable. And when you plug in our input into our function, we get our price. So the item is not a function of the price. The price is a function of the item. Again, these are all of our possible output values representing our range. This slide is just on using function notation. So you are very comfortable with looking at y is equal to some expression. But from function notation perspective, y is also known as f of x, which is the common variables that we use, but you'll also see h of x, g of x, p of x, p of t. It's just being able to clearly see what you're inputting into the function in order to spit out your output value. Now let's go ahead and look at our second example where we want to use function notation to represent a function whose input is the name of the month. So our x values are month names. So think January, February, March, April, May, June, all the way up to December. And then our output value is the number of days in that month. So 31 days in January. And then it also says we are assuming the domain does not include leap years. So for January or for February, it will just be 28. And then December, it's 31. So we want to come up with some function notation to represent this. So we're going to have, why don't we let n of d represent our output, our number of days. And then we have our input, so d is equal to our month name. So we can write n of d is equal to our month name. Here, I'll write month name and then equals days, number of days in that month. We can set this equal to y, what we're spitting out. Okay. So let's keep going. Let's move on to our next example where we're able to interpret function notation. We have a function n is equal to f of y gives the number of police officers n in a town year y. And we're asked, what does f of 2005 equal to 300 represent? Well, if we know that our n gives the number of police officers, then 300 is the number of police officers. And y gives us the year. We have 2005 is our year. So we can write this as there are 300 police officers in town in the year 2005. And we're done. Representing functions using tables. So a very common way to see functions is in a table format. So an X, Y, sometimes you'll see it as like a T chart. And how can we figure out if we are indeed looking at a function or a relationship? And it goes back to, again, understanding your definition of a function, which means no x values can be repeated. So if you see an x value that is repeated, fails vertical line test, it's not a function, and we're done. So now we're going to take a look at example 4, where we have 3 different tables here, tables 6, 7, and 8, and we're asked, do any of these represent a function? So, are there any repeated x values? In our first example, all of our x's are different, so we have yes, a function. Second example, all of our x's are once again different. We have yes, also a function. You'll see that our y values are repeated in this table 7, but that doesn't mean it's not a function. It just means it's not a special function. It's a function still, just not a one-to-one function. Whereas in the first case, we have a function and it's special because it's also a one-to-one function. However, in that last table, table 8, our x values are being repeated, which means we don't have anything. We don't have a function, and most certainly it's not one-to-one because it's not a function at all. So x values repeated, therefore vertical line test fails. And we do not have a function. Okay, and we're done. Second objective, finding the value of a function. And this section, I will say, students usually pick up very quickly on, so it won't be too bad. We simply are given our input value and we just want to plug it into our function to spit out our output and simplify. So in this example 5, we have 4 different parts, A, B, C, and D. And the function that we're using here is x squared plus 3x minus 4. So wherever you see an x, I'm actually going to draw some parentheses. And then finish up the entire function. Now, we are going to be using this for each part of this problem. A, B, C, and D. The only thing that's changing now are your inputs. So in part A, we're plugging in 2, calculating and simplifying. 2 squared is 4, 3 times 2 is 6. 4 plus 6 minus 4 just gives us 6, and we're done. In part B, we are going to be plugging in A squared plus 3A minus 4. And we are done. None of these are like terms, so we cannot simplify further. In part C, we're going to be plugging in our A plus H. A plus H in parentheses squared is just utilizing your FOIL method, first, outer, inner, last, which is just a special form of distributive property. A times A gives you A squared. A times H gives you a plus AH. H times A is the same as another AH. And then H times H gives you H squared. We'll use distributive property distributing the 3 as well, so we get a plus 3A plus 3H minus 4. And we can combine these two like terms. And so when we do, we get A squared plus 2AH plus H squared plus 3A plus 3H minus 4. There are no other like terms to be combined, so we are done. And then last but not least, we're asked to evaluate this whole expression, which is, you'll soon learn when you eventually get to calculus that this is part of the definition of a derivative. It's just we don't have that limit as h approaches 0 in front. So how do we evaluate this? Well, we have f of a plus h, which we plug in our a plus h, and we're actually going to have to put in 2 of these. So maybe I'll do that right now. And then I'll shrink this so this is all on the same row. It's going to be a little small, but I think you guys can see it. I'll move this over a bit. Okay. So we have our a plus h minus our f of a. So we want to make sure this whole thing's in parentheses because we're going to be distributing. I put the parentheses in the wrong spot, right over here. forgot the minus. So we have minus f of a. And our f of a is what we had in part B. And this is all over h. So what's happening here? We have our f of a plus h, which is what I have highlighted in yellow. We solved in C, minus our f of a, which we solved in B, all over h. So why don't we just plug in those values? And we're going to notice that a lot of cancellations take place. So yellow minus blue, and we want to make sure that our blue is again in those parentheses because we are distributing this negative to each term inside the blue all over h. And I'm going to zoom in on this now for you. When we distribute that negative, we can easily see that our yellow a squared and our blue negative a squared cancels out. Our yellow positive 3a and our blue negative 3a cancels out. And then our yellow negative 4 and blue positive 4, after the distribution, also cancels out. And so what are we left with? We're left with 2ah plus h squared plus 3h all over h. Now we can clearly see we can factor out an h from each term in the numerator. And when we do, we're left with 2a plus h plus 3 all over h. H divided by h is just 1. So our final simplified result is just 2a plus h plus 3. And we're done. Difference quotient. So we just completed a difference quotient problem. In our example 5, this part D was difference quotient. The only difference between this part D and our notes on the next slide is the fact that we were dealing with A instead of X. That's just a different variable. There's no difference, or it doesn't make a huge difference. And so anytime you're dealing with a difference quotient problem, it's important to first compute that f of x plus h or a plus h and simplify that to your best of ability. And then you want to subtract your original function from that, simplify those to your the best of your ability by combining like terms, and then see if you can factor out an h, because if you can, then you can cancel out that denominator h and have it in fully simplified form. Example 6. So in this example, we are given a function and now we want to solve for all of our possible input values, aka all of our possible p-values. So let's do some substitution. Our h of p is the same as 3. So we can rewrite this as 3 is equal to p squared plus 2p. We're going to go ahead and subtract 3 from both sides so that we can clearly see that we're looking at a quadratic expression here. Quadratic equation, actually, because it's equal to 0. And now we can factor out this left-hand side. This just factors into a p plus 3 in parentheses p minus 1, which then by our zero product property, we can set each of these binomials equal to 0 so that we can solve for our two potential values of p. And so we end up getting p is either equal to -3 or +1. And let's check to see if these both work. -3 in parentheses squared gives you 9. Plus 2 times -3 is -6. 9 minus 6, that gives you 3. So that works. Now let's plug in 1. 1 squared is 1. Plus 2 times 1 is 2. 1 plus 2 gives you 3. Both of these solutions work, and we're done. Evaluating functions expressed in formulas. So, if you're given a function in equation form, you want to write its algebraic formula. And what we want to do here is we want to solve our equation by isolating that output variable and figure out what is on the other side, seeing if we can simplify it further and find all of our solutions. There's just one note that I want to mention. It's important to note that not every relationship expressed by an equation can also be expressed as a function, so we just want to be mindful of that. Now let's take a look at our example. We want to express this relationship as a function where our p is equal to f of n. So we want to isolate our p here. I'm going to rewrite the problem. So we're looking at 2n plus 6p is equal to 12. I'm going to subtract 2n from both sides. So we're looking at 6p is equal to -2n plus 12. Divide both sides by 6. So we have p is equal to -2n over 6 plus 12 over 6, which is just the same as -n over 3 simplified plus 2. And then last but not least, we know that our p is the same as f of n. So we can write this as f of n is equal to -n over 3 plus 2. If you realize this is very similar to our whole y equals mx plus b form, so we're actually dealing with a linear function here, where our slope is -1/3 and our y-intercept is 2. Now we want to evaluate functions given in tabular form, also known as just table form. We have a few examples, I believe, on the next page. Yeah. Showing functions in tabular form and how to evaluate if we were to ask, or if we were to ask you to find like g of 1 or f of 10, or find our input value if f of x is equal to 3, for instance. And so this is just the step-by-step procedure and how to do that, but we'll go through it on this next example in concrete form. So our part A is asking us to evaluate g of 3. And so what that means is wherever you see the 3 value in our n row, we want to figure out what our output value is, which is 7. So g of 3 is just simply equal to 7. Whereas in our part B, we're now given the output value of 6, and we want to figure out, okay, when our output is 6, what is our input? We have two possible solutions here. We have 2 and we have 4. So our two solutions are 2 and 4. And we're done. Let's evaluate some function values from reading a graph. And so if we're asked to find f of 2 here, we want to figure out, okay, when our x value is 2, what is our y value? It's 1. And then we're also asked if our y value is 4, what are our x values? Well, we have 2 in this case. We have x is equal to -1, and x is equal to +3. And we're done. Third objective, whether a function is one-to-one. One-to-one, remember, this is our special types of functions. AKA, we need it to pass both the vertical and horizontal line test. I'm putting VLT and HLT for short. And so our formal definition of a one-to-one function is a function in which each output value corresponds to exactly one input value, meaning that all of your x values and your y values need to be unique. And so there's a little typo down here. We should have a heading. This first diagram is an example of a one-to-one function, whereas the second diagram is a non-example. We still have a function here, it's just not one-to-one. So, all right, still a function, just not one-to-one. Because it passes our vertical line test, it just fails our horizontal line test. Whereas in the first example, it passes both the vertical line test and our horizontal line test. Okay. So it's important to remember we need it to pass both the vertical line test and horizontal line test for it to be a one-to-one function. And it's very logical, right? For each x, we have its own unique y, 1, 2, 1. Our famous one-to-one functions are linear functions, right? The linear functions will always pass the horizontal line test. The only exception is what? Our horizontal line. It fails it everywhere. So now let's look at example 10. We're asked, is the area of a circle a function of its radius? And if yes, is the function one-to-one? So first off, area of a circle. Remember the acronym to find circumference and area. Remember, circumference is just special word for perimeter of a circle. Cherry pie is delicious. Area, apple pies are too. So we don't need the first one. We're really honing in on that second one. And so the area of a circle, pi r squared. Ooh, we're looking at a quadratic function. U-shaped parabola. And are all quadratic functions functions? Yes. So the first part we have is yes, the area of a circle is a function of its radius. And then the second part of the question asks, is it a one-to-one function? And so you might immediately say no, because looking at this parabola, it fails the horizontal line test. But we're talking about circles here. And the radius in any circle is always positive. AKA our input values are always positive. And so if we're looking at a quadratic function that stems from our origin 0, 0, we are going to be neglecting all of our negative input values and just focusing on our positive values and 0. Meaning, does this green highlighted part of the function pass the horizontal line test? Yes, it does. Therefore, yes, our function is one-to-one. And we're done. Our fourth objective is really just formalizing our vertical line test, but at this point in the lesson, I think you have a very strong understanding of our vertical line test. It essentially works by drawing a vertical line along your function and making sure that that vertical line only hits the function in one spot. Because the second it hits it in two different spots, it is no longer a function. It fails the VLT, the vertical line test, and we can conclude that it is not a function. So in our example 11 here, we want to apply our VLT to see if we have functions. In our first example, which happens to be a cubic function, it passes our vertical line test, and I'm actually gonna use green for it passing, right? So passes VLT, therefore a function. Second example also passes. Therefore, a function. But in that third example, straight off the bat, it fails. Hits in two different spots. Therefore, circles are not functions. Horizontal line tests determine if we have our special functions, our one-to-one functions. So I just don't want to repeat colors. We'll use purple here. And so you have to keep in mind one-to-one function includes the knowledge that we also have a function at hand. So all one-to-one functions have to pass the vertical line test in order for it to be a function. But the one-to-one tells us it needs to also pass the horizontal line test in order for it to be a one-to-one function. And so on this next slide, looking at our example 12, we are going to apply our horizontal line test to determine whether we have a one-to-one function. So that first example, straight off the bat, it hits it in 3 different locations here. Therefore, it fails our horizontal line test, and we do not have a one-to-one function here. But in that second example, it passes. Our horizontal line test. Therefore, we have a function. More importantly, a one-to-one function. Okay. And so we're almost done. This was our last example for this section, but our 5th objective is to just really zoom in on our toolkit functions, also known as parent functions or famous functions. And I highly recommend you guys making flashcards on these types of functions because if you have a good visual of what these types of functions look like when we eventually get into our transformation unit, you'll be able to pull from this visual and then transform from there, meaning apply reflections or stretches or compressions or shifts, horizontal shifts, vertical shifts, and it'll make it much easier on you guys and be less overwhelming. So we have our famous constant function, horizontal lines, our identity function, which also happens to be a linear function. Our absolute value forms that V. Our quadratics are those U shapes, or if it's upside down, caves. Our cubic, this is when our 3 zeros are at 0, but if the zeros, aka the roots, are unique, for example, I'll write another example. You have like x plus 4, x minus 3, x minus 5. Then you'll be looking at something a bit more pronounced. Cannot draw right now. Like this, where you can clearly see you have 2 humps here, 1, 2. Whereas a quartic function has 3 humps. So the number of humps is always determined by that highest degree exponent minus 1. So this is maybe x minus 4. Let's do x plus 4, x plus 1, x minus 2, x minus 3. Okay. So 4th degree, which means 4 minus 1 gives you 3 humps or bumps, and so on and so forth. A 7th degree polynomial will have 6 humps going. And we'll learn about end behaviors very soon. And then some more toolkit functions. We have our reciprocal function. I see this one a lot on exams, especially final exams. Our reciprocal squared, our square root, very common. I also see square root and cubic functions, the one on the previous slide on exams, and our cube root functions. Okay. So this was our last slide for our section 3.1. I do hope this was helpful, and we'll be learning about our next section in the next video. I will see you guys soon. Take care.